Hello everyone, I hope you can hear me. It's Gareth Tucker here. I'm the chairman of the IMechE Railway Division Northwest Centre. I'd like to welcome you to the first of our 2021 lecture programme. We hope to give you a full lecture programme this year. As you can see, we're doing this one online. We'll continue to do that for the next 2 or 3 until the end of this year, and we'll review that as we go. Tonight we've got a interesting lecture from Matthew Hack, who I'd like to welcome, previous chair of the Railway Division Northwest. Matthew currently works at the West Midlands Metro, which opened in 1999, operate between Wolverhampton, Snow Hill, Birmingham and other local centres. In 2016, extension through the centre of Birmingham to New Street opened. Matthew's had a varied career, having moved from power generation into rail. He's worked with special purpose rail vehicles, turnkey railway system, and had a spell with Network Rail in infrastructure before finding his home in light rail. Firstly in Manchester Metrolink, and moved, I think it was 2 or 3 years ago, to West Midlands Metro as head of engineering. Thank you, Matthew. If you'd like to go ahead with your presentation.
Thank you for that introduction, Gareth, and that potted career history. As Gareth said, I'm Matthew Hack, Head of Engineering for Midland Metro Limited. Midland Metro Limited is the operator and maintainer of the West Midlands Metro light rail system, operated and maintained on behalf of the owner of the system, which is the West Midlands Combined Authority. In this evening's presentation, I'm going to cover some geography and history, and then go on and look at some technical subjects. So I'm going to describe the West Midlands the geography for the benefit of those who aren't familiar. I'm going to talk about the railway origins of the present light rail network. I'm going to talk about the plans, the current and future plans for expanding the network. Then I'm going to move on to some technical issues, thinking about the subject of systems thinking and how you design one part of the system affects another part of the system. So the topic will be the relation between substation spacing and overhead line. Finally, I'm going to tell you about what hopefully many people will be interested in, which is our onboard energy storage system, or OESS. This is the battery that powers the tram through the sections where there's no overhead line. And this is a UK first to have a rail, as it were, or a light rail vehicle in service permanently with battery power. So moving on to the beginning of my presentation, for the benefit of you who are not familiar with the geography, the West Midlands is centred around Birmingham, which is here. And in more detail, the next slide will show you what the West Midlands Combined Authority it comprises. So we have the population centre of Birmingham in the middle, Solihull and Coventry to the east, Wolverhampton to the west. And in between Wolverhampton and Birmingham, the boroughs of Dudley, Sandwell and Walsall. From the perspective of the light rail system, the axis between Wolverhampton and Birmingham is the area we're going to concentrate on. Now, this rather fuzzy slide, I hope it will become clear what it is. This is the West Midlands round about 1900. So the darker areas are the population centres, the lighter areas are countryside. And it should hopefully become clearer now that we have the centres of Birmingham and Wolverhampton at the top left and bottom right of the picture. And then in between Birmingham and Wolverhampton, we have the population centres of West Bromwich towards Birmingham. Well, we have Bilston, Wednesbury and West Bromwich in a line between Wolverhampton and Birmingham. Up to the north east we have Walsall, and to the southwest we have Dudley. And the areas Dudley, Bilston, Wednesbury, Walsall, Wolverhampton are what's known as the Black Country. And then, so in the in the middle of the 19th century, as railway lines were opening all over the country, a railway line was opened between Birmingham Snow Hill Station and Wolverhampton Low Level Station. This was a Great Western Railway route, and it in fact connected Paddington Station in London with Birkenhead on Merseyside. And that service operated for the next kind of 100 years or so. That was followed by connections off that line from the Wolverhampton direction and from the Birmingham Snow Hill direction to connect Dudley. So you have a local rail network connecting those areas. And in their heyday, this is Birmingham Snow Hill Station with a hotel that was at the front of the station. And then on the right-hand side, we see Wolverhampton Low Level Station, quite grand in its time. None of those buildings shown in these pictures are there anymore. And then just to round off the 3 points of the triangle, this is an aerial view of Dudley as we see it today. Dudley is kind of built on a hill. The town centre is to the bottom left of the picture. Just above that, we have Dudley Castle and Dudley Zoo. And then just to the right or to the east of Dudley Zoo, there's a green space. I'll just move on to explain that. That is where the former Dudley Station was. And we can see there a picture of Dudley Station as it was in the 50s. The infamous beaching cuts basically saw to it that basically during the 60s, it was decided that these lines were superfluous and they were closed. Part of the reason for closing the line shown in blue here is that the line in orange joining Birmingham and Wolverhampton was the London North Western Railway, and that was electrified, and it was felt that the Great Western route was no longer needed. So once those lines had gone, we were just left with if you like, the West Coast Main Line, and then in light yellow at the bottom, following the former Great Western route up to the Hawthorns and then turning down to connect to Stourbridge. So the situation remained like that. However, the route between Birmingham, Snow Hill and Wolverhampton, the bit with no railway, was not built on and was not developed. In 1981, the West Midlands County Council and the West Midlands Passenger Transport Executive formed a joint planning committee to look at light rail, the potential for light rail. In the summer of 1984, they produced a report entitled Rapid Transit for the West Midlands. And basically that was the germ or the seed for all the subsequent development that happened since. Construction of the line joining, there were acts of Parliament, an assent for the conversion of the Midland Metro Line 1 followed on from this. And construction started in 1995 at a cost of £145 million, which is probably almost unbelievable when you think how much these things cost in today's money. So in May 1999, the line opened between Birmingham and Wolverhampton. Birmingham Snow Hill, should I say, and Wolverhampton, once again connecting the population centres of West Bromwich, Wednesbury and Bilston. It should also be mentioned in passing that other plans for developing routes included Walsall. However, that's so far not come to anything. So that is kind of the history of where we got to up until the start of the 2000s and the present day. So during the 2000s, further plans were put in place to extend the network, and in 2010, powers were obtained to extend Line 1 from Birmingham Snow Hill into New Street Station. And subsequently, during the 2010s, during the last decade up to now, powers and business cases have been put in place and developed to take the system to the next stage, basically. So the blue line there represents where we are today, which is going from Wolverhampton City all the way through the centre of Birmingham to a stop called the Library, and we'll explain a little bit more about that later on. The pink lines are either under construction or in design, and they're fully funded. The next area for focus for development will be an extension out to, on the eastern side of this schematic, to Birmingham International and the HS2 interchange on the edge of the Birmingham conurbation. The Birmingham East Side Metro extension will take in the HS2 High Speed 2 railway station in the heart of Birmingham. So just to describe a little bit more how we've got there and the timing of where we've got to. As I said, in May 1999, we reached Birmingham Snow Hill. May 2016, which is just over 4 years ago, we reached Grand Central tram stop, which is outside Birmingham New Street Station. And when the line extended to Birmingham New Street Station, it came right into the heart of Birmingham City, and we saw patronage leap by in the region of 20 to 30% over the previous sustained level. And that is the banner opening the Birmingham City Centre extension in May 2016. That contract was a classic design and build contract with a very traditional contractual arrangement. The decision was made in view of the uncertainty, complexity of the future extensions and the difficulty in time in defining a scope, to adopt a partnership approach. So the present and subsequent extensions will be built by the Midland Metro Alliance, which is a partnering arrangement between the West Midlands Combined Authority, design organisations including Aegis, Tony G, construction organisations mainly led by Colas Rail. And the Midland Metro Alliance have actually delivered the first project that they delivered on behalf of the West Midlands Combined Authority was relaying the track in the street running section of the West Midlands Metro near Wolverhampton. But the first line opening that they delivered was the extension into to the Library tram stop from Birmingham New Street Station or Grand Central. So in December 2019, 2 new tram stops were added to the route. And what's notable about those 2 tram stops is they are on the first wire-free section of the light rail system. There will be further wire-free sections, but this is the proof of concept, and we've been operating very, very successfully and reliably up till now from December 2019. So moving on in the city centre, the next extension will be to Edgbaston in 2021. I have an artist's impression of that coming up. Out to High Street Derrit End in 2026, taking in the HS2 station to Wolverhampton railway station in 2021, probably about a year's time. Anyone who's been through Wolverhampton recently will see that the new station, the very modern and up-to-date design as shown in the picture there, is already in place. They're putting the finishing touches to that, and the final part of the extension will start construction in January or February of next year for the metro route and the tram stop. Edgbaston Village, as I've mentioned previously. So, and then I'm just going to go back to my 1900 map and talk about how we're getting to Dudley. So we have our existing line, and what I'm going to show next is the too quick. So here is the historic route to Dudley, and then I'm going to overlay over the historic route to Dudley the new route to Dudley, which is the pink line. So you can see that it takes in 2/3 of the route of the 1860 route or thereabouts. It takes in most of that, but it goes to Wednesbury instead, and that's the former rail route, mostly used for freight, coming from further south through Dudley and going all the way up to Walsall. So once the Wednesbury to Brierley Hill via Dudley route is opened in 2023, the people of Dudley will once again be able to go on rails between Wolverhampton and Birmingham. And this is the slide I showed earlier of Dudley Station, and I'm going to overlay on that the new tram route, which comes in over the old station where there will be a tram stop, and then up the hill, that's Castle Hill in the bottom left of the picture, into Dudley town centre past the bus station. And this is a more detailed map of that route, showing the all the tram stops, and of course there are many more tram stops than there would have been stations in previous times. Now the next slide I'm just going to skip over, and I'm going to move on to the technical part of my presentation, and I'm going to talk about some systems concepts in design relating the consequences for overhead line of the way you design your substations. So substation spacing. So the first slide that I'm going to put up shows a sort of schematic diagram of the West Midlands route between Wolverhampton and Snow Hill, Birmingham Snow Hill, about 20 kilometres or so. The black line is simply the gradient profile. It looks like you've got some very steep gradients there. They're not in fact steep at all. It's just the way the scale compresses the gradients. You'll see that the whole line, the elevation is a true elevation in meters, so we range between 120 and 170 meters, a 50-meter difference. So it's largely a very level line in practice. But what's noticeable about it, particularly compared to other light rail systems, is that from 1999 for 15 years we operated with substations. The substations were actually numbered. So moving from the left, we have substations 2, 3, 5, 7, 8, and 9. I beg your pardon, 2, 3, 5, 7, no, try again. 2, 3, 5, 6. 2, 3, 5, 6, 8, and 9. So 7 is missing and 4 is missing. and they should go where the gaps are. So evidently, during the late 90s, there was some value engineering took place, and they realized that they could get away without substation 4 and without substation 5 if they just put more copper up in the air to compensate for the lack of substations. And if you compare that, if we compare that to a comparable system, which what I've chosen is one line from the Manchester Metrolink, the Altrincham line. I've put it on the same scale. You can see that the total variation in altitude is only 20 meters for the Altrincham line, so it's very level indeed. The stretch of interest is between Trafford Bar and Altrincham, and the spacing there is about 4 kilometers, the maximum spacing. So in Manchester, they thought they could get away with a 4 kilometer spacing, and even that was considered quite large. And subsequently, a new substation has been added at about the 6.5 kilometer mark, and that was put into operation in 2017, I think. So this is quite a busy slide, and this is just comparing in numbers the substation spacing figures. So moving from the top, in the top of the slide, we have West Midlands Metro Line 1 from 1999. We've got 1, 2, 3, 4, 5 substations, and the widest spacing is between substations 6 and 8, and we have an 8 kilometer gap, and that gives us an average substation spacing of 3.8 kilometers. Comparing that with the Manchester Metrolink Altrincham line, they operated from 1992 till 2017 with 4 substations, should I say 5 substations over a 10 kilometer route with an average spacing of 2.3 kilometers. And then in 2017, they added another substation, giving us a spacing of just under 2 kilometers. I'm going to show, so then in 2014, substation 7 was introduced, and that reduced the average substation spacing to 3 kilometers. The reason for introducing substation 7 is that 2014 coincided with the introduction of the new CAF Urbos 3 tram fleet, which replaced the Ansaldo, the fleet of Ansaldo Breda T69 trams. And very broadly speaking, in terms of both weight, capacity, power requirement, the CAF trams are in the region of 20 or 30%. They're 20 or 30% longer, 30% more passengers, 30% more power. So that substation was essential. Now, there are plans to increase the service frequency, and even the current substations are, there's not much margin. There's very little margin for out of course or degraded running with the current substations, and there's no capacity for increasing the timetable frequency. With the new lines opening, there's potentially looking at increased frequency of tram operation along line 1 as the different centres are joined up. So we may need to introduce more substations, and some outline design has been done for that, which will take us down to a substation spacing of 2 kilometres. So just to look at one of the issues that you face, I'm just going to talk about touch potential. What we see on this diagram is at the top, you've got the substation converting 11 kilovolts of AC into 750 volts of DC. The DC supplies the overhead line and the tram on the right-hand side. The current path goes from the substation around through the tram, along the return path along the running rails, and back up to the substation. I've drawn a little graph there that shows that as you move away from the substation along the rails, you've got 0 volts at the substation, and as you go away, move further away from the substation, according to so volts obviously is amps times resistance. V equals IR, where R is proportional to the distance. The further you are away, the bigger the resistance, hence the bigger the voltage drop. And the consequences of that are shown on the next slide, where if you had, historically, if we had 2 of our new trams halfway, and 2 trams halfway between substation 6 and substation 8, each one drawing 1200 amps, you would have a touch voltage of around 60 or 70 volts, which is quite unacceptable. We should really be keeping the touch voltage down to about 30 or 40 volts. So I should just explain a little bit more about the touch voltage. That's the actual potential of the tram itself above Earth. So if you're on the tram with a touch voltage of 70 volts, when you step off onto the platform and form a contact between the tram and the platform, there's a potential that you may suffer an electric shock. So when we've introduced substation 7, we see that with 2 trams drawing the maximum current, we've reduced the maximum possible touch potential down to about 30 or 40 volts. So I've just got a diagram here which shows the the substation spacing once we've introduced these additional substations. Substation 4 at the 4 kilometre mark, and then we've got a substation 6A and a substation 7A. What are the consequences of saving money on substations for the overhead line? So in order to talk about this topic, I do need to mention that there are 2 main ways of connecting your overhead lines to the substation. And if you like, from a light rail perspective, there's a traditional way which is based on heavy rail practice, and the modern way which is more conventionally used on tram and light rail systems. So you'll see in the yellow diagram at the top, we have the substation feeding a bus bar, and the bus bar has 4 circuit breakers coming off it. And we're separately feeding the up line in each direction and the down line in each direction. So I can isolate any combination of those lines. So let's say, for example, I had a fault on the up line let's assume that the Birmingham direction is to the right. We had a fault on the up line in the Birmingham direction. We could keep the down line energized, and therefore we could do single line running if there was an operational issue. The modern way of connecting light rail up, and this is echoed both in Manchester Metrolink. The old lines were separately fed. The new lines are fed in parallel, and that's going to be the practice on the West Midlands Metro as well. So the advantages you can see in the lower diagram is that you only need 2 circuit breakers instead of 4 to feed the lines. You'll see that I've drawn a vertical line connecting the up and the down, and that's for paralleling. That helps you parallel the lines. And what that shows you is that if you've got 1 tram on the up line, it's actually fed by, in theory, twice the amount of copper that you're feeding a tram in the upper diagram. So the tram on in the upper diagram on the up line has got 1 wire supplying the current. A tram in the lower diagram has got 2 wires feeding the current. Moving on, I've got another busy slide, so I'll need to talk through this. So the yellow highlighted boxes are lines which are, oh, the colour's changed a bit. It's gone from yellow and green to yellow and grey. So the yellow boxes are where you've got a line separately fed on the up and down. The green boxes are all paralleled up. On the left-hand corner of the slide, I have a traditional cantilever. The cantilever is the overhead is attached to the overhead line pole, and in this case we have a cantilever which supports both the up line and the down line, because for some reason we've not been able to put a pole on the other side. Best practice would have a separate pole for the up line and a separate pole for the down line, but for various reasons, due to local constraints and geometry, that may not always be possible. And then on the left-hand side of the slide, just above the cantilever, we see some statistics that tell us that if you have copper contact wire that's 150 millimeters squared, it weighs 1.33 kilograms per meter. If you have contact wire that is 120 millimeters in cross section, it weighs just over 1.1 kilograms per square meter. So if you use the larger section contact wire, it's something like, well, it's obviously 30% heavier. So the consequences of that, so I'm looking at, now I've gone up to the top box in the picture where we have a double cantilever on the Midland Metro, and I'm suggesting that it might support up to 40 to 45 meters of length, and in order to sustain sufficient power delivery and to reduce to sustain sufficient power delivery over an 8-kilometer distance, we actually have twin contact wire. So we don't just have one contact wire which the pantograph draws its current from. We actually attach two contact wires together, so we actually have 300 millimeters of cross-sectional area to deliver the current. And then in addition to that, we have a parallel feeder that runs alongside the contact wire, because you can't make the contact wire any heavier, giving with an additional 120 millimeters cross-sectional area. Now that poor cantilever is supporting, so it's therefore supporting 4 contact wires, 2 in each direction, 2 parallel feeders, 1 in each direction. When you work out the kilograms per a 45-meter stretch and then convert that into kilonewtons, you have a downward force of about 3.3 kilonewtons. In the city centre line, which was opened in 2016, as I've said, the decision was taken to parallel up the up and the down lines, or the Wolves and the Birmingham bound lines, if you like. And as a consequence of that, and you've got parallel feeder that is no longer supported on the cantilever, but buried in ducts running trackside. So therefore, you're only supporting two contact wires. So your vertical load is reduced considerably to about a third of what it was. Then, for comparison, on the Manchester Metrolink, we have various figures there, but the figure that interests me the most is the bottom one, which is almost all of the post-2010 extensions in Manchester. They don't use twin double cantilevers much, and you've got 120 millimeter squared contact wire instead of 150. So the downward force on your cantilever is only sort of 500 newtons, or if it was a double cantilever, then it would be, it'd be up to 1 kilonewton. So the point is that we have stretches of the Midland Metro overhead line where there's a lot of weight on the cantilevers, and one of the consequences of this is that as temperatures rise and fall, and with the passage of trams, the whole overhead line wants to shift in one direction or another, but it's constrained by all this weight. And part of the consequences of that is that then transfers load into the supporting elements. So this is a picture which actually shows you what it looks like with with a double cantilever, and you can see how long that is. We've got the Wolverhampton bound lines, the Birmingham bound lines, and then we've got parallel feeders off the cantilever as well. And there's been some problem here which our colleagues in Orange are having a look at, and you've got a tram that's stuck. It has to be said that the original design had the parallel feeders sitting on the cantilevers, and over time, following 1999, after opening 1999, various modifications were done, one of which was to try and move the parallel feeders off the cantilever wherever possible and onto the OLE stanchion itself. The next slide shows a double cantilever in the city centre extension. You can see it's much lighter, only 1.2 kilonewtons of vertical load, as opposed to, in other words, 1.2 kilonewtons vertical load instead of 3.3, a third of the load, again with the parallel feeders in ducts. And then the next little picture that I'm going to show you in the corner is an example of the overhead line arrangement on the Metrolink Bury line, where we have a single cantilever, and that is supported by a physical stay at an angle, providing much better support, which is a better design, really. All of the Metrolink cantilevers are supported by stays tied to a point above the cantilever further up the pole. So the consequence of this design for the overhead line is that we've had more than our fair share of issues with basically dewirements. Dewirements should really only happen once in a blue moon, once every 3 or 4 or 5 years, something like that. Here are some headlines. I'm just going to show you some headlines from the local papers. This is one in 2015, I think. There's another one in 2016, another one in 2017, another one in 2018, another one in 2019. And the lesson there is that when designing a turnkey system such as the West Midlands Metro, you really have to think of it as a system, and you cannot design the parts of that system in isolation and then let other parts of the system follow on afterwards as best they can. I'm now going to talk about the onboard energy storage system, a little bit about how it's designed, its sort of configuration, and how it's used in practice. So, and of course, it would be remiss of me not to tell you a little bit about, well, not quite so new trams. The trams went into service in 2014 to 15. The length is, overall length is 33 meters, maximum speed 70 kilometers an hour. Mass, that's a fully laden mass, by the way, of 56 ton. We've got 2 motor bogies, one at each end, a trailer bogie in the middle, 4 motors per bogie, each of around 80 kilowatts, capacity 52 seated, 156 standing, giving 208 in total. When the tram was procured, the potential for retrofitting batteries was considered. It was one of the requirements. So when the trams arrived in 2014-15, they did not have the batteries fitted. A contract was subsequently let to CAF to fit the batteries. The trial fit, or the first tram was sent to Zaragoza in Spain, where the trams were manufactured, to have the battery fitted, and then subsequently the retrofit of all of the trams was carried out on site at the West Midlands Metro depot in Wednesbury in a dedicated building, and that was done by a team who came over from Spain specifically for the purpose of doing that job. And the retrofit took place sort of mainly between 2018 and completed early in 2019. And the point being that by the time the extension to the library opened, which was the wire-free section, we had sufficient trams to operate the full timetable. So why OESS? Why use a battery? One of the considerations is aesthetics. So we can see here Birmingham Town Hall, and there's a plaza area around it, completely uncluttered by overhead line poles and wires and the general spaghetti in the air. So it's very pleasing from the town planner's perspective. The other obvious advantage is that you can save on capital cost during construction. You don't have the cost of the substations, you don't have the cost of the overhead line, and furthermore, if there are civil structures where there are constraints such as low bridges, it potentially avoids the need maybe to reconstruct a bridge, and advantage is taken of this, for example, in on the Wednesbury to Brierley Hill line. However, the batteries themselves are not free. They have their own high capital cost, and if you have to replace the batteries soon, it could, over the longer term, the cost of repeatedly replacing the batteries, maybe every five or 6 years, when you do your long-term financial calculations, you might find there isn't a whole life cost saving, but it certainly saves on initial cost. A little bit about the design of the battery system. It's an optimization exercise, taking into account the operating conditions, the timetable you want to run, the number of tram stops, the infrastructure, how many curves you have, how many gradients, what kind of speed you can operate. The point being that, in fact, the operational speed under the battery is 50 kilometers an hour maximum as opposed to 70. And then what size and weight of battery can you actually put on the tram? So arguably you want to put as big a bigger battery as you can on the tram, but there are obviously constraints of space and constraints of weight. In our case, the battery is on the roof, and that raises that's going to restrict the amount of weight that the design of the car body shell can sustain structurally. So there's an iterative process whereby the town planners and the civil engineers, if you like, or the accountants will say, this is the infrastructure, this is the length we'd like you to run without batteries. And then the operations people say, this is the timetable, and these are the tram stops and so on. And then you say, well, that will lead to a battery of a certain size, and that battery's too big for the tram. So we go around the circle and say, well, okay, so we'll have to modify the infrastructure design. Looking at that process in a little bit more detail, so in order to accurately size the battery, we have to run some journey simulations. So the journey simulations take the inputs of the tram characteristics curves, gradient, stop, speed limits. The tram characteristics are what the inverter can deliver in terms of power, what kind of current it can take. And then over on the right-hand side, we have a diagram showing maximum speed limits at different locations along the route. There's no point in designing the tram for the top, sizing the battery for the top speed of the tram if you're never going to go at top speed on the route you're interested in. You've got to consider what gradients. There's much less energy is absorbed, obviously, running on horizontal or near horizontal routes. And then the outputs of this, so the graphs I'm showing on the right-hand side are kind of meant to be representative of what you would see. So you've got a graph there in the middle showing the current draw as you go along the route, and then you can see that you've got a current draw which is mostly positive, but it is negative at certain points, so therefore you can actually recharge the battery as you're braking, and you can recharge the battery as you're braking going downhill. And I have actually witnessed that as you go downhill on a very steep section of the route in the city centre called Pinfold Street, you can actually see the battery charge going back up again, which is quite nice to see. And then the bottom graph shows, it's indicative to show that you need to understand the decay of the battery, the loss in battery charge as you follow the route, the chosen route or the desired route. And then when you're modeling the system, you have to look at the normal case, which is average passenger load, average auxiliary power, and then maybe one extended dwell per trip. The tram stops unexpectedly for some reason, which is quite foreseeable. And then you have to consider the worst case situation with the maximum passenger load, the maximum auxiliary power, several extended dwells per trip. And you have to demonstrate that you can meet the worst case scenario, not on every occasion, but you can't exceed the constraints for the worst case scenario. And then thinking about the constraints, we've got the headlines constraint, which is minimizing the total cost of ownership, which is about balancing the investment cost of the replacement of the batteries with the saving of the money on civil and power infrastructure. And then at a technical level, the constraints are going to be, well, an obvious one: the battery has to supply the required energy and power for the route. And then to prolong or preserve or maximize battery life, we want to operate in a region between 95 to 55% of full charge. We don't want to drop below that to the sort of 55 to 10% range, only exceptionally. Maybe, in an emergency to get you home, but you would design the system such that it can typically run between down to about half full charge under normal operation. And then again, an obvious one is that by the end of the round trip, there has to be enough overhead wires in the air to enable you to restore your charge. There's also the possibility of having discrete charging locations, and this may be required in some places. And then you can't be required to draw more current than the converter will allow you. And then thinking about, so you've got one route, and then if you keep rerunning that route day in, day out, and over a year and over several years, the people designing the battery will see how many charging cycles you're going through, and there's a relation between the number of charging cycles and the total life of the battery. I think we're aiming for kind of 6 or 7 years life. And then moving on to look at the actual configuration of the system, it is originally in grey, you can see what we had there originally. That's the traction converter, which converts the DC voltage to the three-phase AC, which drives the three-phase AC induction motors. And there's a little box there that says, by the way, we've got auxiliary power we're taking as well. That's fed either from the overhead line or from the red boxes, which are the onboard energy storage system. I'll explain the makeup of those boxes later on, but that overhead DC link as an alternative to the overhead line. So this is a close-up, if you like, of the battery pack, and it comprises 4 main modules, which are working from left to right. The DC-DC converter, so you actually have to step up the voltage from the batteries, and then we have ESU1 and ESU2, which are energy storage unit 1 and 2. Those are the battery packs themselves. They're made up of many small batteries cells constructed in serial and parallel. And then at the end of it is a very, very key and important part of the system, the BTMS, as we like to call it, or Battery Thermal Management System. And that provides cooling for the batteries themselves, which the aim is to keep the temperature in the region of 10 degrees to around 30 degrees Celsius for most of the time. Heat is the enemy of battery life. We seem to have a slight pause. So on the left-hand picture there, you can obviously see, the tram, and you'll just see the battery pack fitting very, very neatly on the behind the driver's cab, and there's one battery pack at each end. And what I should mention is that the batteries are lithium-ion batteries, and there's a little table here of characteristics showing that the nominal power for the two battery packs is 200 kilowatts, a peak power of 400 kilowatts. The onboard energy stored is 40 kilowatt hours per box, so 2 boxes per tram or 4 individual battery packs, giving us 80 kilowatt hours in total at the beginning of life. That will go down as the battery ages. So I'm now just going to show you a picture of that in action, in practice, for those of you who haven't had the benefit of witnessing it. So here we can see a tram coming into Birmingham New Street Station, or the Grand Central tram stop. Unfortunately, the view that I can see is a little bit fuzzy. I think you can see the pantograph just going down now. Once the pantograph is down and the driver has confirmed that they're under battery power, it moves off, and it's about to go up Pinfold Street, past the Town Hall and to Birmingham Central Library. And I'm now going to show you the reverse of that in just a moment when the slide loads.
To arrive at platform 2, it's your
So we've now got a tram that's just come down Pinfold Street and it's drawing up to the Grand Central tram stop the central car or central unit. The tram, you'll just see the tram about to come up. Up comes the tram and it's ready to go. The picture on the right of this slide is the Balog tag, or a passive transponder that has a code in it. There are 2 such tags per tram stop. There's, if you like, an advanced tag that tells the tram that it's it's come to a tram stop where it's going to either raise the pantograph and go into an on-wire section, or lower the pantograph and go into battery mode on an off-wire section. So you've got an advanced tag and a confirmed tag, and when the tram is stopped over the, or near stopped over the confirmed tag, when the tram comes to a stop and the tram control software has confirmed the tram is at a stop, then it will either raise or lower the pantograph depending on the requirement. And this really has brought me to the end of my talk. I think we're possibly running a little bit later than we hoped. We had a bit of a late start. There will be time for questions. If I believe there are some questions appearing now. So just to recap, we've talked about the geography of the West Midlands and how it used to be connected together by a railway network, and how that railway network has been replaced by a light rail network, but that complements the original intention of the people who put the railway system in place. I've described how we're going to expand the network. I've talked about how the original design of the system and the spacing of the substations has compromised our overhead line and what we've had to do about it. And I've described the onboard energy storage system. So thank you very much for listening to me. And I'm going to hand over to Gareth now, who will field the questions.
Thanks, Matthew. Thanks for an interesting presentation. It's great to see a bit more about the electrical side of things, which we don't often hear so much in our IMechE presentations. I've got a few questions that have popped in during the presentation. Anyone else that's listening now, you can ask a question through your text boxes. It's a bit unfortunate we can't have a chat back and forth with the questioner and the presenter due to this format, but we'll do what we can to answer people's questions. So, Matthew, I'm just going to ask the questions to you that are coming through. Got a question here from Andy Batters asking about the type of batteries. Are they lead acid or lithium ion or something different?
Yeah, so they're lithium-ion batteries.
And some follow-up question as well from Andy's asking, is there any fire risk with that, and how is that managed?
Yeah, there is the fact that lithium-ion batteries can go on fire, and that's down to thermal management. So there are sensors inside the battery box that will be looking out for heat and local heat spots. And the safety evaluation went through this topic in a lot of detail, and there's a high level of assurance around the thermal management of the battery systems. It is true that I said that you have to maintain the battery between a certain temperature range in order to prolong its life, or to get the best life you can out of it. But it's also true that the thermal management system, in terms of its ability to detect local heat spots, is, if you like, part of the mitigation of the risk of the battery pack igniting.
Great, thank you. Got another question here from John Evans. He's asking, what's the additional weight of each battery box? Or the extra weight of the tram?
Each one weighs about 1.8 tons. Quite a lot.
That's a lot of weight to carry.
Yeah. So one of the factors, actually, in terms of, I should have said the battery box simply being too big, is actually, interestingly, is axle load. That's one of the constraints, is simply axle load. So we've got our maximum passenger loading. So with the maximum passenger loading and the additional weight of the battery, we can't exceed the axle requirement.
You must have some clever equipment in the depot if you need to change a battery that heavy on the roof of the tram?
Yes, Gareth, it's called a crane.
Yeah.
Yeah, we have a lifting frame where we can lift the battery in and lift it out. So in fairness to the designers, they did consider maintainability, and it's reasonably easy, if you like, to unplug the battery, release it and lift it out. If you have a problem with one of the modules, you can lift out an individual module, or you can lift out the whole battery pack. And the battery came supplied with a lifting frame.
Yeah. Right. I've got another question here from Samuel Jones. So he's asking, because the pantograph has to get lowered and raised as you go into the battery operation, is there any extra maintenance that pantograph needs? Or does it degrade quicker than a normal tram pantograph, or is there anything extra to
So, yeah, that's a very good question. So actually, basically we've had to have an uprated pantograph motor to cope with the additional number of cycles. It's considerably more cycles than you would have under normal operation with a tram, where, to be honest, the pantograph just stays up most of the time. It's going up and down. So the answer to the question is yes, we've had an uprated pantograph with a higher specification motor and lifting arrangement, and it probably will need more maintenance as well. Yeah.
So I'm just catching. I've got a few more questions here. Got Andrew Dundas here, who's mentioning a battery electric multiple unit that ran on D-side line in Scotland in the late 50s. I don't know if you're familiar with it. I've not heard of it before. And has anything from way back then ever been transferred into current designs for battery operated trams or rail vehicles that you're aware of?
I have to confess that I'm ignorant of that project, and I suspect it could well have been a lead acid type battery. A lot of the thinking and the design for this project involves optimizing battery life with this particular battery chemistry, which I imagine is probably quite a bit lighter as well than a lead acid battery.
Yeah. Got another question here from Sam Evans. He's talking about he's went into a bit of detail about substation spacing. He's asking, is there a business case analysis been done for the number of substations versus going to a higher line voltage? And a sort of connected question is, could you have different line voltages on different parts of the network?
Well, you absolutely can have different line voltages on different parts of the network. If you think about the Eurostar that went on 750 volt third rail DC to 25 kilovolt AC, and I think it ran at, is it 33 and a third kV or something over, and so to have electric vehicles run at different voltages is certainly possible. I'm not sure I can see the advantage of that specifically. I absolutely can see the advantage of running at a higher voltage. For historical reasons, light rail systems have always tended to be at 750 volts.
Yeah.
And it would be much, much better if they were to run at, for example, 1500 volts, because then indeed, absolutely, you could have the substations much further apart. You'd be taking much less current through the overhead contact wire. So if you ran at 1500 volts, you'd have smaller section contact wire, and it'd have fewer substations.
Yeah, I've got another sort of related question about substation spacing and asking, is the substation spacing itself more important, or is it how many vehicles are connected to each substation during operation? I know it's sort of connected.
That's a very interesting way of looking at it. Yeah, it's absolutely, so when you design, when you do the power modeling to figure out your substation spacing, you have to consider certain worst case scenarios where maybe you've got 2 or 3 trams have come to a stop and they're all, they're sitting between 2 substations and they're all starting up at the same time. That's kind of that's one worst case scenario. The other convention that's worth noting on light rail systems is the so-called N-1 scenario. In other words, if you've got one substation out of service, the 2 neighboring substations should be able to maintain the normal, the normal operation. So you can have any one substation out of service and you can continue to operate normally. I'm not sure if that fully answers the question.
I think.
And what's interesting is that you typically, typically tramways by convention, there's a magic number which is a 6-minute interval. We try and run at 6 minutes because then it's like a turn up and go service, or you run even more frequently. I think there's other services which run at 4 or 5 minute headways, but we tend to run at 6-minute headways. A lot of Manchester is based around 6-minute headways, and that means that with a typical 6-minute headway operation and a typical tram, you do end up with the substations tending to be spaced optimally around a sort of a 2 to 3 kilometre spacing.
Yeah. Just going to ask one more question. I've got a few more that we won't have time to get to, unfortunately. This one's asking about the sort of whole life cost assessment of using the battery to run wire-free around the library, and sort of the difference in upfront costs in the infrastructure and in the trams and the operational cost. I think you also mentioned it's not entirely just about the cost of the tramway, it's about the aesthetics for the city itself as well. Maybe you could comment on that.
It's a very interesting question. I've actually not been able myself to lay my hands on that calculation, but I have a feeling it must exist somewhere. Part of that question is not going to be answered for a few years, in the sense that we're hoping or expecting, the sort of design is for the batteries to last 6 or 7 years. If we get more life out of them than that, we'll be ahead. If we get less life, we'll be behind. CAF themselves, this is new technology. It's new to have battery trams. Yeah. There's not that many out there, and I think part of this question is only going to be answered when we understand better, the performance of the batteries themselves. And will the whole life cost position change as more extensions are undertaken? Well, I think the answer should, in theory, be no. In other words, we've got a desired life for the batteries, which, as I said, sort of 6 or 7 years. And as we build more extensions, we'll want to come up with the same answer as we add the additional extensions.
Great, thanks, Matthew. I think we better wrap up now. We've gone slightly over. Sorry, everyone. I just want to hand over to my colleague Lyndon, who's going to do the vote of thanks. Hopefully, we still got you, Lyndon.
Excuse me. He is connected, Gareth.
We might have lost Lyndon. I think something might be having a problem with the phone. Just give him another couple of seconds to get in if there's a technology problem.
Hello, can you hear me?
Oh, hi, Lyndon. Yeah.
Yeah, sorry, I think I had my AirPods interfering with things. So anyway, yeah, great. Well, thank you, Matthew. That was an excellent overview of the Birmingham system. I mean, Matthew has took us on a good journey there with a good historical introduction to the railways around Birmingham and how the history has developed over that time. And what was interesting was the development of the tram system adopting some of the old railway routes, which is always good to see, and linking up the relations and Wednesbury, which is what trams really do excel at. You know, low capital cost to get into population centres that have been deprived of a rail network, be it from beaching cuts or from just general non-patronage over the years. So that's good to see, and obviously that's building up the economic development of the West Midlands. We talked about the extensions of the library, the wire free, proof of concept operation, and then some of the next steps to Edgbaston Village and Wolverhampton Railway Station, and the route to Dudley as well. We then went into, Matthew went into the comparison of the substations and why that's important, and we had an overview of the differences of overhead wires, independent or parallel feeder wires, and some of the problems that can cause. Certainly, temperature changes was something that was mentioned, and how that transfers loads into the catenary and stanchion and ultimate dewirements. And I think one of the messages that Matthew said there is about thinking about the system when designing overhead wire systems now resolved and put to bed. And I think I did hear from Matthew that some aspects of the Metrolink system were slightly better than the system on West Midlands. Matthew then took us to the OESS, the Onboard Energy Storage System, with the CAF Urbos 3 tram, which was retrofitted with a sympathetic requirement in hand for the town bell and library extension, so that the trams could run on batteries. And one of the messages that Matthew spoke about that was important was the OESS optimization, and how it's important to set this optimal point, which interestingly links back to the effect there that the OESS optimization forces you to think system, because you do need to have that. You do need to have all the parties looking for that optimal point, and people to give way, certainly in the infrastructure side, to make that happen. Yeah, we talked about the OESS optimization further with demonstration of normal gradients and the life of the batteries, which is obviously very crucial, because battery concepts are now very much in the technological limelight, and battery life is one of the critical factors in making the economics of this work. So it'll be good to see how that pans out in the future. And then Matthew showed us and demonstrated the pantograph to battery changeover using the Balog tag and how that works. So all in all, a very oh yeah, one extra thing as well. The extension of the OESS2 is a good aspect. Is obviously again a sign of interconnecting tram systems to the mainline railway, which, because historically tram systems have tended to not go the full distance. So that's a good aspect. So in that with that summary, I'd like to extend the thanks to Matthew in the customary way from the institution. So thank you, Matthew.
Thanks, Lyndon. Would you just like to the program which I've just put up on the screen? You can see.
Yeah. Okay. So just some words from the secretary now. I hope everyone's enjoyed this first presentation that we've done through the WorkCast system. Thanks to Emma Pateman from IMechE headquarters for just helping out with the mechanics of it happening. So hopefully you've bared with us with some of the disruption. But if anyone's got any feedback, please email me so we can get it right for the next event, because it does look like for the foreseeable events up to Christmas, we will be doing it through this WorkCast system. So we will get the links out earlier so people can register for the event as soon as possible, and to give everyone as much time in advance. In terms of our next paper, it will be the chairman's address on the 13th of October. Professor Felix Schmidt, who's the chairman this year, will give his address. So details of the link for the WorkCast will be sent in due course. We do hope as well to start that day or that session with a case study session at 4:30, which is our customary case study session. So we'll be making details of those sessions available as well if anyone would like to join earlier. After that, on the 10th of November, just to give you an advance notice, we've got the rescheduled modern WSP systems. Richard Moore, Director of Engineering for Wabtec, is going to come along and tell us all about WSP systems, as we had to delay that from earlier this year. So without further ado, I'd just like to wish everyone a safe journey home, and hope to see you at the next WorkCast event.
Thanks, Lyndon, and thanks everyone for joining us today. We hope you'll join us at our next event. Thank you very much.